once one of the keyword has passes the threshold, it will trigger the not safe for work filter. And this is extremely problematic because as we said, this keyword is just a mathematical representation of the correlation. It doesn't really semantically mean anything. And for example, we will see a lot of false positives, like the photo of Donald Trump jumping into the pool, will result in a trigger from the filter. And some random abstract image may somehow have some components inside. When going through clip, it also triggers the not safe for work filter. So we start by doing some experiments. We were thinking of if we put a lot of this person does not exist, and then we run through the scoring system with the happy image. Will we ended up finding the happiest person from this person does not exist? Okay. Ooh. So, yeah. Quick demo. So on the left side, you will see the picture that we in real time downloaded from this person does not exist. And on the left side, this is currently the lowest score of the photo, and this is the higher score. And you see that throughout a lot of different iteration, we will ended up sort of seeing the most happiest person. Right now, we have someone like this, and the most unhappy. It's not the saddest, it's unhappy, or like the farthest, or having the most distance between this image, the keyword happy. Okay. Oh, there's another one. Ah, okay. Let's continue. Okay, so now we go into a really interesting question. So now we input the keyword happy, but what if we put other keywords? And then we put different stuffs. And then also run through stock footage. And we have our friend Pedro here. It's funny because it doesn't make sense. But it somehow also makes sense, I guess. But just to keep in mind that this is a really, really important point that we're trying to express. This clip model is the foundation of most of the image generation model. So if we have a woman as a higher score in nurse, definitely in the image generation model, we could have that generated. And this is the danger that we are trying to propose. And also at the same time, they are a certain artistic quality that they're looking for, like a grape is not art at all, but a random firework has a higher correlation to the keyword art. And thus is the bias that we were proposing. And then we ended up inputting different keywords and then do like a softmax comparison between them. This random AI-generated face has a really high similarity score to Aboriginal Australian. And also this image of schnitzel has a higher probability between Chinese and European. It makes sense for us, but this is us putting our own bias onto this image and onto this mathematical space.
I think one thing that's very important, this list of ethnicities, we took it from the US Navy, so it's not our list. We didn't make a list of ethnicities. We just Googled for one, and then the US military surely has one, so we just used the US military ethnicity list that you can, when you enlist, cross in which ethnicity you are.
And we put other stuff. It's funny because as a human mind, it makes somehow some sense. But this is the bias that we want to talk about. We are inputting our own bias onto these machines and onto these models. So we put our own faces also. And we put a list of different countries, and then we ended up having the higher score of which name of the country that has a higher correlation to us. And it's funny because we found something called Chad. Oh, I mean, we have to go back to talk about again that it's not a homophone because it's really interesting that mathematically this keyword Chad has double meaning, but at the same time it's us as a human to understand what that means. For the math part, for the latent space, they don't really know. And we try to contextualize it. If we input the keyword with a sentence, in the beginning it says person from the country Canada or person from the country blank, then we ended up having a more proper result. But by proper, I mean it's biased. Also, we put food. It's good that we use our own face. Yes. But that's the point that we want to try to emphasize. Like, what exactly is this model doing? And this is the backbone of everything. So now we understand that if we have enough faces, and then if we go through enough iteration, we ended up like finding the happy face. But the most happy face, again, is just a higher similarity score to the keyword happy. But how about generating a happy face?
Yeah, thanks. If you remember when we tried in our live demo, where we tried to find the happiest and the furthest away from happiest person, we used thispersondoesnotexist.com as our generator, which just gives you random faces. It's admittedly a very stupid generator. It just gives you a random face, and then we look, is it a higher score, and then we keep it or we throw it away. So we already almost built our own text-to-image model, because we can input any text, and then with lots of iterations, it will find a face that kind of fits our description. But like the interesting part is also like we can generate this image on the way by using kind of this similar structure. So kind of we build our own text-to-image model, but Stable Diffusion is a bit more complicated. And we shortly have to go over this slide again. I always find it very funny to look at all of these different representations, because, I mean, we can look at all of them and not understand them. I don't understand them. But at least I found the parts that kind of made sense and are like similar things in these different representations. And there's like different steps that are kind of important or like happen in the pipeline that I could kind of make out in all of these representations. And the first one is that we need to embed the text, which just means you type in a text and you get a very high dimensional vector that you then can calculate with. This is what Clip is used for that. So that's exactly what Ting showed you beforehand. And then the second part is like the actual diffusion, where the image gets generated, and this happens from noise. So we start with like some very colorful image, and then it slowly over time generates the image, trying to follow the text that we input, like mathematically. And then in the end, because I lied to you, all of this doesn't happen with pixels. It happens in some abstract space that we can't see. It has to be converted back into something we can, so into pixel space, and then we have the finished image that we can actually see. And
I want to sort of emphasize again on the embedding part. This is a really important thing that we need to think about. How do we embed the keyword happy into a number? Because we don't, as a human, we have emotions, and these emotions are currently being embedded into a strings of number. This really doesn't make sense. It don't really align with our sentience. But this model works solely because of that, because we could embed different types of keyword into numbers, and then it generates the image.
Yeah, that's very important. Once you have typed in anything, all the meaning is gone. It's all actually bits and bytes. So all the meaning we put into it, if we use text-to-image models, is like the things we perceive. So we put meaning back into it again. And this is like this process. It's also called reverse diffusion. What's very interesting is like the current image, the one on the left, is like the current state of the image. It's an iterative process. If you ever use prompting, you can type in steps. That's like the steps of diffusion it does. Then the thing in the middle, this is actually the thing the model learns, which is just noise, how to generate noise. And the right image is then what it predicts the image will look like. So it's basically the left image plus the noise in the middle equals the right image. And you can see like over time, it slowly goes towards the concept of dog. And this is like happening in a loop. So like step for step, it generates new noise to go towards the keyword, for example, dog. And this is very important. Like Stable Diffusion does not generate images. This sounds weird, but it's actually a very, very sophisticated noise generator. So it generates the thing in the middle. And the interesting thing about the architecture that they used, because we already heard that Clip comes from like the medical field, the UNet structure that generates this noise in the middle also comes from the medical field and was used to segment also X-ray images. So maybe the most advancement was not OpenAI, it was medicine after all. And What's interesting in this process is that you can also say how much should it go towards dog, for example. And you can also, in the code, just like comment out the line. Like, just don't go towards anything. Just do your thing. Just denoise it. Like, just add noise over it and see where it ends up. And this is what we did here. We just cut out the part where it goes towards a concept and let it like denoise itself and see where it ends up. And it's very funny because you can still make out things in there, even though there's like no guidance in there at all. And this is probably the rawest representation of like the latent space, of the raw data in there. Probably the couple down there in the middle is somewhere in the data set. And if there's no guidance, it can just reproduce these patterns and things that are normally not seen. You can also do the inverse. So say, instead of going a very small number towards cat, you can also like do it times 1,000 and get like the cattiest cat, which is even for us not the cattiest cat. But here you see from left to right, top to bottom, we just increased this, go more towards the keyword cat, and you can see very fast it gets outside of our realm of understanding what a cat is. But now back to how did we do these red images, because this is one of the main topics of our talk, is you probably have used image to image, which is the same as text to image, just instead of an text you input an image. And what you can do with this is you can give it an image and then you describe it in a prompt. I want to make this drawing into some fantasy landscape, and then you get a fantasy landscape. But what we did is we input an image, also stock images again, and we didn't put in any prompt. So we just said like, do your thing without anything. And we wrote a small little library that's very shitty, so please don't read the code, and just did this in a loop. So we said, take this stock image, do your thing, then we took the output and we put it back in again. And I mean, we already spoiled you about this. It turned very pink, very quickly. And we were like, okay, how can this be? Is this like a floating point error? Do we have to, I don't know, change like some parameters around? So we just tried again with different models. And it turns out, different models, these are like in the order of their release, Stable Diffusion 1.5, 2.1, XL, and XL Turbo, like the main versions. And you can see all of the models converge into something, but they all have their own favorite color. So choose your spirit Stable Diffusion model now. So Stable Diffusion 1.5 goes into this weird, colorful purple patterns, like Stable Diffusion 2.1, more like primary colors, SDXL, straight lines all the way, and architecture. And Stable Diffusion XL is like this turquoise photography. I can't even describe it. And we were still curious, like, okay, this is still like some calculation error. We are doing something wrong. So we tried it again. There is the strength parameter. So when you do image to image, you can say how much of the original image you want to keep.